this video is the last in the chapter of numerical differentiation. In particular, we're going to talk about the effect of data errors. So one of the major problems when numerically differentiating empirical data is the existence of random measurement errors within the data itself. These errors cause the experimental data to have some natural fluctuations. If the experimental data is supposed to follow a particular model, then the best way to deal with such data is to find the best fit and use the derivatives of the best fit as described in the curve fitting section in Chapter 9. However, if such a model does not exist, for example when measuring the position function of a moving subject, then care has to be taken when dealing with higher derivatives of the data. In particular, the fluctuations are magnified when higher derivatives are calculated. The following figures were generated by first sampling the Runge function in the domain -1 to 1 at an interval of 0.1. Then a random number between -0.1 and +0.1 was added to the points to introduce noise or measurement error. A cubic spline was then fit to the data. And so you can see the original function shown in the figure here. So where the blue is the actual function, and then the black dots are the data with the noise added, and the orange is a spline function fit through a piecewise interpolating function using third order splines fit through the noisy data. The small fluctuations in the data lead to very high fluctuations in all of the derivatives. And in particular, the second and third derivatives do not provide any useful information. You can see the actual derivatives for the second derivative, and you can see that the derivatives predicted by the data are have these wild oscillations and do not provide any really useful information. And you can see that this gets worse as we increase the order of the derivatives. So the first derivatives have some fluctuations. The ones shown here, the second derivatives, it gets worse, and then the third derivatives, it gets even worse. So similarly, the figures here show the results when random numbers between -0.05 and +0.05 are added to the sample data of the Runge function. So when the centered finite difference scheme is used, the errors lead to very large variations in the second derivative. So the previous slide showed taking the derivative of the interpolation function, and here we're showing using the finite difference scheme to take the derivatives, and we get a similar result where the first derivative, the noise in the data is not so bad, but then as we take the higher derivatives, the noise starts to be amplified. So you can see here, this is with the second derivative. We can also see the same thing in the third derivative as well as the fourth derivative, where the fourth derivative here does not really provide any useful information. So one possible solution to reduce noise in the data is to use a filter to smooth the data. So here, a Gaussian filter is used to reduce the generated noise. So again, the blue line is the actual function. The data points are the function with the added noise, and the orange is a piecewise interpolating spline fit through the data points. So this is the kind of original noisy one, and then this is after applying a Gaussian filter. So you can see now that the points and the spline fit through the points are much smoother. So the fluctuations in the data are reduced, and this allows smoother derivatives to be obtained. So this is the first derivative shown here, the second derivative, and the third derivative. And so you can see we have, it's still not super accurate in the areas where the function changes rapidly, but it's much smoother and we have a lot less oscillations compared to the unfiltered situation.